Thank you, Chairman, for your very kind introduction. I'm great honored to be invited to talk on this conference, and my talk will focus on the problem of large-scale wildfires. Different from a normal fire with lower spread rate, a large-scale wildfire is characterized by existence of many types of extreme fire behaviors with very high burning intensity and thus inducing very high spread rate. In recent years, there have been many serious wildfire accidents in the United States, Australia, Brazil, and Europe, and the increasingly serious problem of wildfires has been receiving more and more academic attention. However, many problems remain unsolved, and especially the knowledge on the combustion mechanisms and behaviors in wildfires is far from adequate and complete. I would like to take this opportunity to summarize the current status and the challenges for the future study. My talk will be given in three major parts. In the first part of background, I intend to summarize the essential factors that trigger the growth and acceleration of wildfires, and then I will discuss the combustion problems of several intensely burning behaviors in wildfires. The last part summarizes the challenges for the future study. Based on the finding of a historical study, wildfire is a natural process for over 400 million years. Therefore, in human history, concern with fire problems probably predated the first practical use of combustion. Fire is one of the most common types of disasters with very huge fire cost. Here, fire cost includes the expenses of fire suppression and the damages due to fires. According to the data of NFPA, the total cost of fires in the United States accounts for 2% of U.S. gross domestic product. This slide shows the 10 days average records of global fires since 2014 reported by NASA. Absolutely, the Earth is undergoing intense burning of fires every day. Since the Industrial Revolution, modern combustion science has been targeted to efficiently utilize the energy released from combustion and mitigate the adverse effects of fire and explosion accidents. However, compared to industrial combustion, fire problems have attracted relatively less academic attention with much less progress. Maybe two reasons for this. One reason might be the lower expectations of economic return from fire research, and another one is concerned with the greater complexity of fire problems. The scaling law of burning behaviors reflects a critical complexity of fire problems. Due to the interaction of combustion with heat transfer and atmospheric flow, fires of different scales may have varied mechanisms that cause completely different burning behaviors. The left figure shows the classical experiments of Belinov and Kudyakov in late 1950s on the burning rates of liquid fuels. As shown, with the increase of pore diameter, the burning rates undergo a significantly nonlinear variation. The scales of the fuel cover the range from 1 centimeter until 30 meters. Different scales are dominated by different heat transfer mechanisms. The right figure shows that the flame length of axisymmetric fires varies with the heat release rate by a 2 to 5th power law. Therefore, the flame length is also a nonlinear function of the fuel size. Similar nonlinear trend applies to radiation of flame since it depends on the flame size. Therefore, theories and models of small-scale fires cannot be used to predict the burning rates, burning behaviors of large-scale fires. In other words, a high-intensity erratic fire cannot be considered as a large-scale model of a low-intensity fire. A fact often overlooked is that although large-scale wildfires happen infrequently, they are responsible for the majority of fire-related economic losses and natural resources damages. For example, for all the wildfires in the United States, just the 2 to 3% of out-of-control fires cause 95% of all fire costs. When a mass fire happens, it always provokes a wave of enthusiasm, and people believe that more should be done on fire science. But such beliefs are often short-lived and rarely support profound and persistent scientific endeavors due to the low frequency of such fires. Also, wildfires are among the foremost natural disturbances on the Earth, significantly influencing the ecology and climate change. As estimated, the carbon released in the fire in Indonesia in 1997 accounts for 13 to 40% of the mean annual global carbon emissions from fossil fuels. This is the scenario of the Camp Fire in the US California in 2018. The peak spill rate reached 33 kilometers per hour. As recorded in many reports, the peak spill rates of large-scale wildfires generally fall into the range of 10 to 30 kilometers per hour. However, in the initial stage, any wildfire is mild, with spill rate on the order of only 0.1 kilometers per hour. This is a 100-fold difference and increase. Therefore, there must be some key mechanisms that trigger the acceleration of fire. In science, we should answer what are the essential mechanisms that induce fire spread acceleration and intensely burning behaviors leading to disastrous consequences. To answer this question, we should first understand what is large-scale wildfire. In the laws and the provisions of many countries, large-scale wildfire is often described in terms of large burning areas. In scientific community, there is virtually no strict definition. However, it is commonly recognized that a large-scale fire is characterized by extreme fire behaviors. These behaviors are erratical and dangerous, and usually act as the driving hands to make the fire be out of control. Generally, there are 6 typical extreme fire behaviors. Conflagration is a kind of large-sized flame having definitely moving fronts with large fire sizes and narrow depths. It can move rapidly and burn out vast areas. Firestorm is also a kind of large-sized flame. The horizontal size of firestorm can reach over 100 meters in large-scale wildfires. It thus can produce very great convective activity with very tall convective columns. Different from conflagration, a firestorm often stays on the same place and has little outward spread. Firewall is a vortex-shaped swirling diffusion flame. It is generally induced by the interaction between the local wind field and the flame. In essence, firewall is a kind of concentrated vortex with combustion. In practice, firewall can have a flame height of over several hundred meters, with very high flame temperature, flame velocity, and burning intensity. Firewall may be the highest flame naturally produced in Earth. A crown fire is a kind of special spread mode different from a surface fire. It burns from the ground until the top of the trees, and thus induces very high burning intensity. A spot fire is another kind of special spread mode, denoting the phenomenon that firebrands are lifted from the ground into the sky and to produce numerous new ignitions beyond the major fire area. As reported in the literature, the highest distance of Firebrand's transportation reached around 30 kilometers. An eruptive fire by name means a quick acceleration of the fire spread rate. It usually occurs in canyons or steep slopes. This is the video images of fire in France in 2000. Here is a village. The rapidly accelerated fire covered a wide area of 5 to 6 hectares within only 1 minute. This picture depicts the major behaviors in large-scale wildfires that induce the acceleration and growth of fire spread. The first is the growth of surface fire spread, which depends on the conditions of fuel, meteorology, and topography. The second is the large-size flames, including conflagration, firestorm, and fire whirl. And the third is unique spread modes, including crown fire, spot fire, and eruptive fire. These extreme fire behaviors act as the driving hands, making the fire to deviate from the original mild steady state and undergo a non-steady transition to reach a new steady state with very high levels of spread rate and burning intensities. Most importantly, all extreme fire behaviors are generated by merging of multiple fires. The key role of extreme fire behaviors has been demonstrated by many case studies. A typical example is the Black Dragon Fire in China in 1987, which was one of the most massive wildfires in China during the past 300 years. As reported, the early stage was first dominated by moderate and high-intensity surface fires, following which high-intensity crown fires occurred with numerous spotting and firestorms. The peak rate of fire spread was estimated to be up to 20 kilometers per hour. After that, fire whirls were frequently observed and had key roles in accelerating the fires, causing the fires to finally get out of control. Eruptive fires were also observed after that. Then we come to examine the combustion dynamics of typical wildfire behaviors. We first touch on the surface fire spread. Surface fires are the most common types of wildfires. It has a long history of study since 1940s, with many models developed. The models can be generally divided into statistical models with statistical correlations from laboratory or field experiments or historical case studies. Empirical models in framework of energy conservation, but with empirical data to close parts of the problem. And nowadays, physical models trying to describe the physical processes of hydrodynamics, combustion, and energy transfer. For these models, the basic idea is that the energy is transferred from the flame to the fuse ahead, increase its temperature until the so-called ignition temperature. The key point is that the preheating mechanisms of the fuse. This graph describes the complex heat transfer mechanisms involved in surface fire spread. We can see that radiation could be in the form of flame radiation, amber radiation, and radiation loss. And there may be surface convection, interior convection, convection due to turbulent diffusion, and convection cooling. This table summarizes the major mechanisms considered by different authors. Obviously, very different viewpoints exist, namely surrounding the relative importance of radiative and the convective heat transfer mechanisms. For example, as shown on the left, In the viewpoint of Rosomel, when there is no wind, besides flame radiation, convective cooling due to the indraft of the air should be considered. When there is wind, the convective heating due to flame contact and flame puffing play a part. However, for the upslope fires, Rosomel did not describe the convection ahead of the flame front. For that, our experiments revealed that with the increasing slope, the convective cooling undergoes a physical transition, dominated first by natural convection under lower slopes, and then by combination of natural convection and flame-induced convection under higher slopes. When these effects are considered, from the right figure we can see that the new model predicts well the spread rate under high slope angles. Another challenge is concerned with the uncertainty in physical models of surface fire spread. In the models, the fire spread is often assumed to be in a steady state with fixed flame properties, fixed fuel bed properties, weather conditions, and terrain configurations. However, errors of prediction of spread rate may arise from uncertain, imprecise, and improper determinations of the parameters because of unreasonable assumptions, rough approximations, or inaccurate measurements. Errors may also be caused by different evaluations of the fuel consumption coefficients and heat convection coefficients. From this table, we can see different authors have very different estimations of the model input parameters. This slide shows a parameter uncertainty analysis of my group on a typical model of fire spread. On the right, you can see different flame temperatures were used by different authors, normally within 900 to 1100 K. It was found that the predicted fire spread rate is very sensitive to the used value of flame temperature. Also, the errors in estimating the fuel coefficient efficiency, flame height, ignition temperature, and heat convection coefficients all have remarkable influence on model prediction. A small difference produces a large error. An additional challenge is related to the physical model of fireline in surface fire spread. In the fire spread models, fireline is usually characterized as having constant flame length and flame temperature. There are very few studies to develop combustion models of fireline. In combustion physics, a fireline is a linear or rectangular turbulent diffusion flame. However, the past studies on diffusion flames mainly stem from circular fuel sources. For rectangular sources, an empirical 2-to-3 power law was developed to correlate to the flame length. However, when the heat release rate exceeds a certain value, the power law would change from 2-to-3 to 2-to-5. Recently, we performed line fire experiments in laboratory, showing that with the increase of the flow rate of fuel, the line fire undergoes a transition from laminar to turbulent buoyant until the non-buoyant flame. This overall trend is somewhat similar to that of the round flame. We established a new physical model to predict the flame length of turbulent line fire, in which the flame burning is described by the mixture fraction instead of the heat release rate. Therefore, the model can be more general to be applied. Finally, we obtained the predictive correlation of the flame length by physical derivations. Based on this correlation, when the flame is buoyancy dominated, the flame length depends on the heat release rate by the 2 to third power law. When the fire is momentum dominated, the flame length does not depend on the heat release rate. These results are consistent with the past empirical models, but this new correlation has more general significance with very wide application scope. The predictions were varied by forecasts using 4 different fields. Now let's turn to discuss multiple fires merging. In nature, multiple fires can be generated in different ways: by lightning, by flame radiation, by fire spotting, or by the spread of multiple fire lines. The right figure shows several large-size flame fronts in the Canberra fire in 2003. Assume that by the merging of flame fronts, the spread rate increased sharply. Fire merging is a critical step to accelerate surface fire spread, produce large-size flames, or induce unique spread modes. This slide shows some cases evidences. The left shows that the 2 fire lines spread toward each other and then merge to generate a large flame. Also, fire wall is generated. The right one shows that the spotting fires quickly merge, within only 2 minutes, to form a large flame. The challenging issues include the mechanism of fire acceleration and immersion, and the fire interaction effects on the fire spread acceleration. For any single pool fire, the heat feedback from the flame to the fuel surface sustains the flaming combustion. However, for the multiple fires, they interact with each other via 2 mechanisms. Firstly, the fuel surface of any one fire not only receives the flame heat feedback from itself, but also from the surrounding flames, mainly by radiation. This heat feedback enhancement will make the burning more intense. Or in another aspect, when the multiple fires are close enough, the air entrainment for inner fires may be significantly restricted, which in turn decreases the burning rate. Within certain ranges of the parameters such as the fire spacing, the 2 mechanisms may be comparable or competitive, leading to nonlinear burning behaviors. In recent experiments, the heat feedback enhancement effect has been verified by accurate determination of the radiative, convective, and conductive heat feedback. We can see that with the increase of the flame spacing, the heat feedback is weakened. Also, the air entrainment restriction effect has been verified by velocity measurements. Assume here, the entrainment velocity of the outside is significant, while that of the inside is very low. The fire interaction effect depends on the interval of fires. This slide shows the variation of the burning rate of multiple fires with the spacing distance among the fires. As we can see, the 2 competitive effects of the fire interactions, that is the heat feedback enhancement and air entrainment restriction, they caused the nonlinear variation of the burning rates with the variation of the fire spacing. Also, the flame height varies with the fire spacing and the heat release rate nonlinearly due to the competition of the 2 interaction effects. In recent years, some attempts have been made to develop physics models of parallel line fires based on the BS diffusion theory. The characteristic velocity of line fire is determined by the size and the spacing of fire sources. BS theory usually ignores the effect of buoyancy on diffusion, which makes the experimental data deviate significantly from the theory, assuming the right figure. Therefore, how to physically characterize the buoyancy influence on the diffusion of the parallel line fires remains to be a challenge. Now let's turn to the third, eruptive fire. It means sudden increases of spread rate within very short time. In literature, there are many names such as eruptive fires, blow up, flashover, and fire eruptions. Many fatal eruptive fire accidents were reported, and the most recent was the fire in Moli, Sichuan province of China in 2019 that caused 31 fatalities. We still know little about the mechanism of eruptive fire. Many mechanisms have been proposed, such as the atmospheric instability theory, thermobell theory, gas accumulation theory, flow attachment theory, and the self-acceleration of spread. Unfortunately, many of these theories remain at the level of conjecture with no verification. The gas accumulation theory is associated with the canning terrain. It is assumed that the unburnt flammable products generated by pyrolysis of vegetation or from volatile organic compounds can accumulate in deep canyons. These gaseous products mix with air and then may be ignited by any exterior heat source, which may induce turbulent premix flame or deflagration and cause extreme high spread rate of flame. This seems to be a perfect theory, but unfortunately until today, there haven't any experimental verification on this theory, mainly due to the difficulty of experimental simulations in laboratory. The flow attachment theory is concerned with the upslope terrain. This theory explains that under lower slope, the airflow ahead of the flame front is the indraft toward the flame, which is a kind of convective cooling. However, when the slope is high, the flow from the flame will be attached to the fuel surface, with the flow direction leaving the flame front. Thus, there will be significant convective heating that may trigger the acceleration of the fire spread. In laboratory, we performed the upslope fire experiments with the slope angles of 0 to 30 degrees. It was found that when the slope exceeds 25 degrees, the fire spread rate underwent a sharp increase, suggesting the occurrence of eruptive fire. Also, the data of velocity and heat flux both demonstrated significant convective heating effect. This verified the theory of flow attachment. Recently, we reported an eruptive fire experiment in canyon terrain by collaboration with Professor Dominguez Vigas from Coimbra University. We changed the major canyon slope from 0 until 30 degrees. We found that under different slope angles, the fireline shows completely different evolution modes. When the slope is 0, the fireline behaves like a normal linear flame front. Then when the slope is 20 degrees, the fireline changes to be like a butterfly mode. Then when the slope is 30 degrees, we can see that the firelines on the two canyon surfaces separate to be parallel. You can compare to see the difference. By using the data of velocity and the heat flux, we demonstrated that under this high slope, the spread was significantly accelerated. This was originated by the interaction of the two firelines, which indicates remarkable convective heating ahead of the flame front. This fireline interaction is thus believed to be a key mechanism for triggering eruptive fire in canyon terrain. The future challenging work is to develop physics models for simulating the spatial fireline evolution and fire spread acceleration. We now come to discuss firewall. Case studies indicate that firewall can only be generated when the size is beyond some certain scale and when there is significant convective activity around the flame. Different kinds of facilities have been designed to produce firewalls in laboratory. It is recognized that three conditions are necessary for the formation of firewall: the presence of a generating eddy, the existence of a fluid sink located within the eddy, and some wall friction along the lower boundary of the eddy. In terms of the concept of generating eddy, the facilities can be divided into two types: the rotating screen facility. For that, the generating eddy, that is the rotating field, is naturally induced by the flame burning itself, and the fixed frame facility. For that, the rotating field is produced by mechanical means. Compared to a normal fire plume, a key complexity of firewall is that the flame buoyancy, or the burning rate, and the ambient circulation are strongly coupled, leading to complex burning behaviors. This is the rotating screen facility developed by Professor Howard Emmons in 1960s. This apparatus was mechanically controlled to induce the ambient circulation so that the burning rate and the circulation could be independently controlled. He used the acetone as a fuel, but the fuel size was only 10 centimeters. So the produced flame was essentially a laminar flame. This is the fixed frame facility developed at the Stakey Laboratory Fire Science. It has a height of 15 meters with a horizontal size of 2 meters. There are 4 gaps on the corner with a width of 20 centimeters so that the air can be naturally introduced from the gaps into the enclosure and form the ambient circulation around the flame. For this type, the burning rate and the circulation are coupled. We use this facility to study the combustion characteristics of static firewalls. Besides this one, we also established other types of facilities for different purposes. The rotating screen facilities with different scales, similar to that used by Emmons, are used to study the combustion patterns of the firewalls under different circulations. The air curtain facility with no solid walls is used to measure the flame emissivity by infrared technique. And also the SPIV technology was also used for velocity field measurements. Prediction of firewall formation is important for early warning in firefighting. Lee and Garris used 2 screens moving in opposite directions to study multiple firewalls produced along a line fire. They found that the critical circulation for generating firewalls depends on the heat release rate by a power law. Kuana used an L-shaped fire in a wind tunnel to simulate the firewall in the 1923 earthquake in Tokyo. They also found a power law for generating firewalls. Soma and Saito classified the historical firewalls into 3 types, and they successfully reproduced the 3 types of firewalls in laboratory based on scaling analysis. In our recent study, we found that the formation of firewall is associated with the extension of an initial protovortex formed at the flame tip. Hydrodynamic instability analysis showed that different scales of flames have different critical conditions for generating firewalls. This is verified by experimental and field data. You can see that the theory fits the data of scale beyond 1,000 meters. Many researchers used different facilities and different fuels to measure the burning rates of firewalls. We can see that when the fuel size is specified, the burning rates of firewall are much higher than those in general pool fires. Then we should understand why the burning rate of firewall increases compared to normal pool fire. As we know, the burning rate of a general pool fire is controlled by the heat feedback from the flame. However, for the firewall, the rotating plays an important role. By velocity data, we found that due to the effect of the rotating in the main flame body, there is a balance between the radial pressure gradient and the centrifugal force, so that a steady vortex structure forms. However, in the inflow boundary layer, the wall friction will decelerate the flow so that the radial pressure gradient will be bigger than the centrifugal force. This significantly enhances the convective heat feedback to the fuel surface, leading to the increase of the burning rate. Therefore, this means us that we can develop the model of the burning rate based on the analytical analysis upon the boundary layer equations. In this way, we derived a new correlation for burning rate of firewalls. This couples the mass burning rate with ambient circulation. Here, the factor N depends on the flow conditions. In laminar flow, N equals unity, and in turbulent flows with smooth and rough surfaces, N equals 1 to 1/4 and 0, respectively. Assume in this figure, the correlation agrees well with the laminar firewall data of Emmons and also the turbulent firewall data of my group. This slide shows the experimental data of the centerline temperature of firewall versus the dimensionless height. The radiation errors were corrected. As can be seen that, similar to pool fires, the firewall also involves 3 zones of continuous flame, intermittent flame, and a plume. However, the ratio of continuous flame height to the whole flame height in firewall is nearly 0.68, much larger than the recognized value of 0.4 for general pool fires. In addition, the maximum excess temperature on the center line was much higher than that for general pool fires. Therefore, the flame in firewall is more stable. The temperature and the velocity data are then used to calculate the mass flow rate, which characterizes the strength of L entrainment. It was found that the mass flow rate increases with the height by a power law. Here, the power is lower than unity. And at the mean flame height, the ratio between the mass flow rate and the heat release rate is much lower than the value of pool fires. Also, the value of the mass flow rate to the required mass stoichiometry is much lower. All these results indicate that the L entrainment is always suppressed in firewall as compared to buoyant pool fires. This figure shows the variations of L entrainment coefficient with height. We can see that in the continuous flame, the coefficient is very low, and the mean coefficient within the mean flame height was only 0.01. However, the coefficient at the base reaches 0.3, much larger than that in the continuous flame. This demonstrates that the air entrainment of firewall mainly occurs in the bottom boundary relation. As for the flame height of firewall, many researchers have developed different correlations by scaling analysis, fuse rising time analysis, data fitting, and modifications of classical BS and rubber laminar flame models. Most of them describe the small-scale laminar firewalls with lack of characterizing the complex interaction between the heat release rate and the circulation for large-scale turbulent firewalls. Based on the air entrainment suppression concept, we developed the new flame height correlation, which couples the two critical parameters of heat release rate and the imposed circulation. This correlation was found to agree well with the data in the literature for buoyant and jet flames, and is more applicable than the single parameter models shown here. We also measured the flame emissivity of firewall by the air curtain facility. We found it is significantly higher than that of general profile. We also estimated and found that the soot volume pressure of the firewall is much higher than that of the profile, but first increases with height slowly and then decreases. This may be related to the fuel-rich core of firewall and may be the reason for the high flame emissivity of firewall. Using the rotating screen facility with propane as a fuel, we found that with the increase of the circulation, as many as 9 combustion patterns were found during the transition from buoyant diffusion flame to firewall. All the 9 flame patterns are outlined in the plot of the heat release rate versus circulation, assumed in the right figure. The distribution and the burning behaviors are very complex. For example, when the circulation reaches a certain value, the spiral thin flames at the top merge and give rise to the transient flocculent flame. The flocculent means that the flame was not closed at the top, and there is no evident interface between the flame and the plume. The conical flame was topped by the cylindrical flame. With further increase of imposed circulation, we found that the flame height decreased while the flame diameter increased. This is consistent with the firewall in UK in 2018. Now let's discuss spot fire. The whole process of spot fire consists of 3 sequential sub-processes. That is the generation of firebrands, the firebrand lofting and transport, and ignition of recipient fuels by firebrands by either flaming or smoldering. For firebrand generation, very few studies touch on the analysis and modeling of the thermo-mechanical mechanism of firebrands. For the limited studies, the breakage model considered the thermal decomposition model, and the distinct regime were identified to describe the effect of combustion on the breakage mechanism. Various factors such as size and types of fuels and local gas velocities were considered. However, the current study has not been connected with the extreme fire behaviors. As we know, firebrands usually originate from intensely burning behaviors such as firewall, firestorm, and conflagration. Therefore, connecting these behaviors with firebrand generation is a big challenge for the future study. For Firebrand lofting and transport, the major purpose is to predict the maximum spotting distance. In the available studies, different flow fields have been considered, including burning trees, line thermals, wind-driven surface fires, active crown fires, firewall, turbulent swirling natural convection plume, and so on. Some model simulations have investigated the impact of the turbulence on the transport and the deposition of firebrands in a turbulent boundary relation. More work needs to be done on modeling combustion-induced decay of firebrand in forced convection. Hot particle theory is usually used to investigate the problem of firebrand ignition, in which the key parameters include the fuel type, moisture content and density, particle temperature and diameter, wind velocity. In a recent study, we found that the ignition boundary follows a hyperbolic relationship between the initial particle size and the particle temperature. Smaller particles require higher temperatures to ignite the fuel. The studies indicate that firebrand ignition process is a complex problem involving physical and chemical processes in the solid and gas phases. Therefore, by more fine models of physical and chemical processes, more work needs to realize more accurate quantification of the effects of firebrands, fuels, and ambient atmosphere. We turn to summarize the challenges of the future study for wildfire. The primary complexity of large-scale wildfires stems from the significant physical and chemical interaction of combustion with heat transfer and atmospheric flow in all the intensely burning behaviors, which determines the nature of highly nonlinear behaviors and mechanisms. Despite significant advances in exploring wildfire phenomena and behaviors for more than 1 century, there are still numerous known unknowns in this domain. The fundamental understanding aiming at application tools capable of dealing with large-scale fires remains at its early stages. So we should be aware of how much we know of the known unknowns associated with wildfire acceleration mechanisms. Thus, the first challenge is theoretical elucidation of nonlinear behaviors in wildfires. Different intensely burning behaviors in wildfires are controlled by various mechanisms depending on the fuel, meteorology, and the topography conditions. The growth and acceleration behaviors of fires may be controlled by several mechanisms simultaneously, but are usually dominated by one or several mechanisms. Accurately modeling different intensely burning behaviors relies on the theoretical elucidation of the nonlinear essence relevant to the significant interactions among fluid flow, radiation and convective heat transfer, and combustion. The second challenge to be addressed is the critical conditions for the generation of different behaviors. This topic essentially deals with the non-steady transition from a steady-state behavior to a new steady state with changes in controlling mechanisms. For example, the transition from individual fires to fire merchant is associated with changes in heat feedback enhancement and air entrainment restriction. Compared to a normal pool fire that is generally controlled by buoyancy, a firewall is dominated by the interaction between the generating eddy and the burning of the flame. Although there have been some efforts to clarify the critical conditions For the generation of fire margin and firewalls, the existing theories and models remain not satisfactory for the complete solution of forewarning problems for these intensely burning behaviors. The relevant studies highly depend on new experimental design to simulate the real scenario of the transitions between different behaviors. For example, recently we designed such a scenario where multiple flames constitute a square, with gaps at the corners so that the entrained air induced by the central fire can enter into the enclosure, thus imparting a rotation flow around the central flame. Assume that the burning intensity and the flame height increased with time due to the interaction among the fires, and a stable ambient circulation was thus established around the central fire, leading it to undergo a transition to become a vertical firewall. Evidences from the literature concerning with the laboratory experiments, field observations, and case studies reveal that different burning behaviors have a close relationship. We plot this in terms of all the available evidences. You can see different behaviors can be induced by different other behaviors. The critical conditions for triggering different behaviors by others remain to be a big challenge. The third challenge is related to approaches to wildfire modeling of different scales. In the operation tools of surface fire spread currently in practical use, the interaction between the fire and atmospheric dynamics is not considered. For a large-scale wildfire with intense burning, the energy released may be strong enough to drive the atmospheric dynamics over a wide range of spatial scales, and thus it is of importance to consider the coupling between the fire and the atmosphere. Some efforts of this aspect have been made, like the model of fire attack. However, generally, empirical models of fire spread rate are used to close the problem. More accurate predictions of the response of the fire to the ambient winds and the atmospheric response to the buoyant fire plume are the big challenge for the future study. Thank you for your attention. I would like to thank many people in this work. Deep thanks to Dr. Koyosato for his fruitful collaboration with us when he worked at my group as a visiting scientist during 2006 until 2016. This study has also massively benefited from Dominikus Vigas and John DeRees. The authors want to express special thanks to Iwan, Ishu, Albert, Simeone, and Sarah, who contributed valuable discussions and suggestions for the improvement of this paper. Thanks also go to Rantu for his assistance, as well as Mark Finney, Kozo Saito, Jesse, Oleg, Arno, Alexander for their support. This work is funded by the Natural Science Foundation of China.